For the next book, we got a book on differential equations, a dynamical systems approach to the theory and practice by Viana and Espinar. And it's a graduate book on the theory of differential equations. And it starts off with local solutions, where it covers the existence and uniqueness theorem and Peano's existence theorem. This is a bit more general. And it covers maximal solutions, where we extend solutions, numerical integration, and autonomous equations. For example, the Poincare recurrence theorem, which I know is one of Mira's favorites. Autonomous linear equations, where we have topological classifications of hyperbolic flows. Non-autonomous linear equations. We got Lyapunov stability, Grossman-Hartmann theorem, stable manifold theorem. We got vector fields on surfaces and the Poincare-Hopf theorem. We also have quite a lot of applications. Like we see here, we have the oxygen ozone cycle as application. Here we have the shooting methods. We have planetary systems. So yeah, it's a book that I think is very nice for me, because it does relate to applications and not only pure math theory. It really, I think it's really good book for self-study. And there's plenty of exercises as well. So yeah, this is a very good book that especially appeals to me and somebody interested into the foundation of differential equations without really wanting too much manual solving. But yeah, pretty cool book. The next book is a book on basic partial differential equations by Bleeker and Xordas. Bleeker is the same guy as the one who did the Atiyah-Singer theorem book. And I think this is one of my favorite books on differential equations, on partial differential equations. But it's not a book for mathematicians, it's more a book for physicists. So it covers first order PDEs, the heat equation, Fourier series and Sturm-Liouville theory, the wave equation. Then we have Laplace equation, Fourier transforms, numerical solutions of PDEs, and PDEs in higher dimensions. So yeah, I really like this book a lot because there's a lot of very cool applications, and it does show you the basics, and for somebody interested in physics and also the math. So for Brouwer, for example, this would be a particularly good book to work through. Very nice, even though I guess the problems are a bit on the computational side, but there are some theory as well. So, but yeah, really like this book a lot. One of the favorite things in this book is this one exercise where he kind of shows. Here is this one. Is this exercise where he kind of shows that there can be no orbits, no planetary orbits in higher than 3D space. The three-dimensional system that we have right now for everything wouldn't really work. The Kepler's laws wouldn't really hold in there and anything. So the solutions we get right now are pretty much only for 3D. A very nice application, very nice exercise, and the book is filled with exercise like this. So especially for some. So I mean, Mira wouldn't enjoy this book really, but somebody into the physics will really like this. I think you really see that this is a really good book. Next is one of the only combinatorics books I have. But Crimson already worked through it, so it's Discrete Calculus by Marikanda and Tonolo. Extremely good book. I really like this book, even though I don't really like combinatorics too much. So it starts with counting, sequence, and collections, occupancy constraints, inclusion, exclusion, Stirling numbers and Eulerian numbers, manipulations of sums, formal power series. It has generating formal series and applications, recurrence relations, linear recurrence relations, symbolic calculus, Euler-Maclaurin formulas of order 1 and 2, and the Euler-Maclaurin formula of arbitrary order, and then finally Cauchy and Riemann sums, factorials, Ramanujan numbers, and their approximations. Why is this book named Discrete Calculus? Because there is a way to basically generalize calculus to discrete situations as well. The discrete integral will just be summation, and the discrete derivative is just going to be the difference between two subsequent sequence elements. And then you can basically generalize a lot of calculus that way. And it's really beautiful. It's really something that I like a lot. So differential equations become difference equations. The number E, Euler's number, becomes the number 2. So yeah, you can really, and it really is not only like pretty, but it's also useful. Because you can prove a lot of summations that way. You can prove a lot of very nice stuff this way. So I think, when it comes to combinatorics books, this is really one I actually like, because I think it does everything in a way that I would like, where they try to give a bit more overarching theory instead of just cool problems to solve. Here you see the discrete primitive and everything. This can actually be justified with measure theory, because you got the Radon-Nikodym theorem, and the Radon-Nikodym derivative for the discrete measure, for the counting measure, just is a difference. So all of this is measure theoretically sound, which I think is pretty nice. So yeah, if you're into combinatorics and you want a combinatorics book to do, highly recommend this book. The only problem with this book is that it kind of lacks a bit of exercises. Like there are exercises, but there's often like a theory piece of like 50 pages of theory before you come to like 15 measly exercises. So that's a bit of a downer, I guess, for the book. The book should really have more exercises, and it should be like subdivided over sections instead of chapters. But yeah, it's kind of a minor complaint. Next, another really great book. We have here primes of the form x squared plus ny squared, Fermat, class field theory, and complex multiplication, third edition with solutions. So you have a book by Cox, another one of these books by Cox, which are a really great series of books. We have from Fermat to Gauss, we have class field theory, we have complex multiplication, and we have additional topics. So yeah, it's a book basically on algebraic number theory, and like every single one of Cox's books, they're like really great, really good books. I think everybody interested in number theory, or at least algebraic number theory, would want to work through a book like this. Highly recommend it to basically everybody. It's really close to the book by Edwards, the Fermat's last theorem book, but still I think it's worth doing both books in a sense, because again, the Edwards book treats things historically, and this treats things more from a formal perspective. So Crimson, if you ever want to do this book, I'm very down. Next comes a book on by Shittik, The Sufi Path of Knowledge, Ibn al-Arabi's Metaphysics of Imagination. It's basically an ancient book on Sufism. So we see theology, see ontology being treated, epistemology, hermeneutics, soteriology, and consummation. Just basically a book on Sufism and their worldview. I have not worked through the entirety of this book yet, but it's pretty. It's a pretty book. Next, one of my favorite complex analysis books, but it's part 2 at least. It's Complex Analysis 2 by Freitag. I also have, this is about Riemann surfaces, several complex variables, abelian function, higher modular functions. This is basically the sequel to number 1, which I also have, but might present a bit later. So its first chapter deals with Riemann surfaces, the harmonic functions on Riemann surfaces, uniformization, compact Riemann surfaces, analytic functions on several complex variables, abelian functions, modular forms on several variables, and then some algebraic tools in the appendix. Mirror, I know that you like Stein and Sakarki a lot, but I think Freitag really is a really great book on complex analysis. I think it's a perfect book on complex analysis. I don't know any book which does things as thorough and as good as Freitag does. So yeah, I'm very happy with this book. I'm very happy. I've worked through these books, and I think they're absolutely great. They're absolutely fabulous books. And this book goes pretty far. It even proves the big Picard theorem. It covered the fundamental group and everything. So yeah, very good books. Next we have a book by Weintraub, Galois theory. Pretty short book on Galois theory. It starts with field theory and Galois theory, development and application of Galois theory, extension of the field of rational numbers, further topics in field theory, then some results from group theory. Pretty short, basic book. Didn't really work through it, to be honest. I'm not sure why I have this in the first place. I think because Weintraub is a really good author. I really like Weintraub, but I mean, I didn't think this book was anything special. Next, the following book is by Hoffman and Morris, The Structure of Compact Groups, a primer for the student, a handbook for the experts. A very, very thick book on compact groups. So yeah. Topological groups, so it also covers Lie groups with a lot of topological groups. So we have basic representation theory of compact groups, where they do like the Haar integral, the Haar measure, the ideas of Peter and Weil, characters, linear Lie groups, compact Lie groups, duality of abelian topological groups, compact abelian groups, structure of compact groups. We have compact group actions, the structure of free compact groups, cardinal invariants of compact groups, abelian groups, that's already appendix, covering spaces and groups, a primer on category theory, select result of topology and topological groups, measures on compact groups, and predictive limits of well-ordered inverse systems. This is basically the reference work for everything related to topological groups, at least compact ones. Pretty good, pretty very, very well written and good exercises. I'm not sure this is. I used to be very into this kind of stuff. I'm not really anymore. Not sure I would ever complete this book. But yeah, I do think it's pretty good. It's pretty good. And then finally we have Kedison and Ringrose, Fundamental Theory of Operator Algebras. This is volume 2 of 4. It covers operator algebras. It does comparison theory of projection, normal state and unitary equivalence of von Neumann algebras, the trace algebra and commutant, special representation of C-star algebras, tensor products, approximation of matrix algebras, cross products, and direct integrals in decomposition. It's a very difficult book actually. The exercises were very difficult for me. I'm not sure I was a fan of the notation, but it does cover a lot of things. Like it's amazingly comprehensive, and I do like the book for that. It's like it just really has everything that you wanted to have.